So welcome everyone to, it's the second talk, I think, in the special seminar series on surveys and space exploration. And we're very lucky today to have Bill Chaplin from the University of Birmingham to come and talk to us about Astro Seismology and Helioseismology in particular. So Bill did his PhD at the University of Birmingham, where I did my first postdoc, where he worked on high precision radial velocity data. He then moved on to be an European Space Agency Fellow in ESTEC in the Netherlands. And then he went back to Birmingham, where he became a permanent fixture. And he is now very senior in many of the sort of space missions like TESS, Kepler, and Plato. And he's also one of the main people that kind of started the revolution of helioseismology using the Birmingham Solar Oscillations Network. And he was recently made the head of School of Physics in Birmingham, which is great for Bill, but maybe not so great for people that want to chat to Bill because he's now very busy. But it's a real pleasure that we've got him here now to talk to us about his work in helioseismology. So take it away, Bill.
Thanks very much, Ted. All right, let me share my screen. So yeah, thank you very much, Ted. Thanks for the introduction, and thank you everyone for joining today. So as you can see from the title of my talk, and also as well from Ted's very nice introduction, I'm going to be talking today about results that we are getting on the sun, but also as well as the stars, where we're using oscillations of the sun and those stars to actually probe their interiors. But here what I'm going to do is actually focus on the insights this is giving us on the outer layers, the envelopes of these stars, with relevance to activity and the solar cycle and stellar activity cycles in those stars as well. So from even though the title says probing the solar cycle with BiSON, and I'll come on to what BiSON is in a moment, the subtitle there suggests there is some stellar stuff, and actually there's a pretty big dollop of stellar stuff. Actually, it's about half and half. So I'll begin talking through what BiSON is, what helioseismology is, then what Astro Seismology is, and then what we'll do is we'll have a look at how we're using some of these data to tell us something about essentially about dynamo action in these stars and the cyclic variability that we can detect using these data. So let me begin with BiSON. BiSON is an acronym. Of course, as astronomers, we love acronyms, and this is an acronym that we've had in place since the 1990s. But actually, this network has actually been collecting data, actually going all the way back to the 80s, kind of as a network. But actually, we have data from individual telescopes that actually take us back into the 1970s. So we've got a really, really long and pretty unique set of data here. So this is a network of ground-based telescopes that make Doppler velocity observations of the sun. You can see there from the map on the right-hand side the locations of the observatories. I'll come back to show some more pickies in a minute of some of the observatories and say a little bit more about them. But crucially, what these data give us access to are data on the sun's natural oscillations, and using those oscillations to infer something about the structure of the sun and its properties is a field that we call helioseismology. So helioseismology, the oscillations that we observe in sun-like stars, and of course the sun is the prototype of this particular class of oscillator. They arise as a result of sound waves that are actually trapped within the sun. So we get standing sound waves set up. It's actually near surface turbulence associated with the convective envelope, and actually turbulence right at the surface of the star, where we see a so-called pattern of granulation. That gives rise to the generation of turbulence and sound. That sound gets trapped within the body of the star. The sound is generated across quite a sizable range of spatial and temporal wavelengths. And we get standing waves set up within the star, of course, because stars are big balls of plasma, big balls of gas. The standing waves actually give rise to rhythmic periodic oscillations of the star. So the little graphic I have here is representing just a simple radial mode of pulsation. But what we find is that in sun-like stars that we actually get a really rich spectrum of both radial and non-radial pulsations excited to observable amplitudes, and also as well many harmonics of each of those different radial and non-radial modes as well. So as we'll see in a moment, by actually measuring the frequencies of all of those oscillations, also the splittings of the frequencies as well due to rotation, that allows us to actually build up a very detailed picture of the interior of the sun, both in terms of its hydrostatic structure, but also as well its internal rotation. So that's what helioseismology is. And actually the discovery that the sun is undergoing constantly these rhythmic periodic pulsations, that discovery was actually made by my predecessors in Birmingham. And they actually made that discovery with kit on the roof of the building where I have my office at the moment. Now you can see there that this, from the slide, helioseismology is in the English dictionary. And also in there as well is the definition Astro Seismology. So that's simply when the more general case of applying these techniques to stars other than the sun. So the discovery that the sun is oscillating like this actually dates back to the early 1960s, but the recognition that the entire sun pulsated, that we had these whole sun globally coherent pulsations, that discovery was made in Birmingham in the 1970s. The amplitudes that we get due to the rhythmic pulsations of the sun are really, really tiny. So we can observe the Doppler shift associated with the surface of the sun effectively moving towards or away from us, or alternatively, we can measure changes in the brightness. So as the star breathes in, it gets hotter and brighter. As it breathes out, it gets cooler and darker. The sorts of changes in brightness we're talking about for sun-like stars are of the order of few parts in a million. And that's why it took until the 1990s for oscillations in other stars to be discovered. Similarly, if you average the Doppler velocity perturbations that you get due to oscillations across the visible disk of a distant star, you get a net disk average signal of the order of a few centimeters per second. And that's varying on a time scale of the order of a few minutes. So again, that's why it took so long for the precision in Doppler velocity observations of other stars to be good enough to be able to detect the oscillations. And of course, a lot of that drive in terms of technology that came about as a result of course, efforts to detect exoplanets orbiting other stars. So we kind of piggybacked off the back of that. So I'm going to go on as well and, excuse me, talk about and show some results from the NASA Kepler mission. Kepler's been really transformational for us in that it provided exquisite micromagnitude precision data on literally thousands of these sun-like stars where we could measure the oscillations. Prior to the advent of Kepler, we had detected solar-like oscillations in other sun-like stars in maybe a handful of stars. And Kepler gave us data on the order of something like 1,000 stars. So it's really opened up our ability to be able to use these data. And just to comment as well, the relevance of our data that we have on the sun and the connection to the data that we get on other stars. The telescopes in our network observe the sun as if it was a star. So we do not spatially resolve the surface of the star onto many pixels. So again, remembering we're measuring the Doppler shift, but we don't actually resolve the shift at all. We basically average the signal that we get from the sun over the visible disk. So essentially the data that we get are like the data we would get on a distant star. The reason why that was done historically when these data were being developed is actually the instrumentation was originally developed to try and detect planets around other stars. And the discovery that the sun was undergoing these periodic pulsations was a completely serendipitous discovery. And that opened up the field of helioseismology thereafter. So the data that I show you on the sun are directly relevant, directly the kind of data that we get on other stars as well. So just some photographs of some of the other telescopes that we have in our network. So all but a couple of them are actually robotic telescopes. So they're some of the first actual robotic telescopes that were deployed anywhere in the world in the field of astronomy. So the first of the automated telescopes that we deployed is actually the one on the top here. So this is an image of our station in Carnarvon in Western Australia, which was historically the site of a satellite tracking facility that was used during the Apollo program. Bottom left, we've got our site in the Andes Mountains in Chile, Las Campanas. And then bottom right is our site at the South African Astronomical Observatory in the Karoo Desert. So again, these are all automated telescopes that are providing, day in, day out data on the Doppler velocity, disk average Doppler velocity shift of the sun. And it's from those data that we measure the oscillations of the sun. So if we take a typical day of data from one of these observatories, the raw signal is dominated by the rotation of the Earth. So as the rotation moves, effectively moves the observatory towards the sun in the morning and away from the sun in the afternoon. If we subtract off that signal, which gives a Doppler shift of the order of a few hundred meters per second during the course of a day, we end up with data that look like this. So here what we've got here is 3 strips representing the 3 8-hour segments of a single 24-hour day, where we've subtracted off that large shift, and these are the residuals that are left over. And you can see it kind of looks a bit like a seismograph trace. So essentially what we're picking up here, these are the oscillations of the sun, the so-called 5-minute oscillations of the sun, because that's approximately the dominant period. The different colors here represent data from different observatories. So again, we have observatories at a range of longitudes around the Earth. That gives us continuity of our data, which is very important. And also you can see as well periods where we get overlap. So where some stations are collecting data simultaneously. And if you look very carefully, you can see during those periods of overlap that the signal looks remarkably similar, as it should do. One other thing you can see here as well is that the sort of what looks suspiciously like evidence of beats. So essentially what we're seeing here is the combination of several tens of overtones of both radial and non-radial modes. So what we tend to do in terms of the meat and drink, in terms of the analysis, is to construct a long time string or long time series from these data, again from the data from all the sites, compute the frequency spectrum, and you end up with something that looks like this. So this is a classic example of basically the 5-minute oscillation spectrum of the sun. Notice the frequency along the bottom axis. So the peak power there is a frequency of around about 3000 microhertz. That's roughly a period of 5 minutes. And you can see we get this beautiful spectrum of overtones. Here we're seeing both radial and non-radial modes and their individual patterns of overtones. And essentially what we do by measuring the frequencies of these modes, which are formed by sound waves within cavities inside the star that, for example, penetrate to different depths, this gives us the ability to be able to build up a very detailed picture of the not only the radial, but also the latitudinal structural profile inside the star. Also as well, the non-radial modes are split due to rotation, so we can build up a similar picture of what the sun looks like inside dynamically, so what its rotation profile looks like. So it's measuring these frequencies, that's the key thing to what we do. So it's basically giving us access to and being able to see what the sun looks like inside. It was only with the advent of helioseismology that we were able to, of course, be in a position to properly test, if you like, and not just infer what is really happening inside the sun. Again, a lot of the focus of what we do is, of course, on understanding and advancing our understanding of stellar evolution theory. In particular, at the moment, a real challenge for us is understanding the evolution of rotation in stars like this. But what we're going to focus on today, what I'm going to talk about, is how we can use these data to say something about the activity in these stars. And in particular, evidence of cyclic variability as well. So of course, the solar cycle is driven by the solar dynamo. And this in turn, an important element of this is the differential pattern of rotation that we have in the outer convective envelope of the star. So the outer third or thereabouts by radius of the sun is convectively unstable. And it's the differential pattern of rotation there, and also as well the very sharp transition from differential rotation that we see in the outer envelope of the star to something like solid body rotation in the radiative interior, that very sharp transition as well, that helps to play a role in basically winding up the magnetic field and giving rise to the sorts of structures that we see that are aligned essentially parallel to the equator that we see at times when the sun is very active. So that's the image on the right-hand side here, where we have stuff that's aligned in what we call a toroidal pattern, where we see this sort of structure of, so here this is showing essentially emission from the corona, but this maps down as well to the location where we're seeing this very, very strong emission here. That maps down at a photospheric level at the surface of the star to where we see sunspots. Okay, so of course this comes and goes in the solar cycle with an 11-year periodicity in terms of absolute levels of activity. But the sun cycle is actually, strictly speaking, 22 years long, because as well we get a change in sign as well of the magnetic fields in the north and south, northern equator and southern equator as well. So what we're going to talk about, and I'm going to go on to talk about, is how we can use the fact that as the sun's activity changes, that has an impact on both the frequencies of the oscillations, but also as well it changes the energy in the oscillations. And from that, from measuring those changes, we actually then have a direct diagnostic of activity in a star and activity in the sun. But also because, of course, again, the modes are formed by sound waves that are trapped in cavities inside the star, it's giving us access and insights on this changing activity through directly probing what's happening essentially in the outer layer of the star, just beneath the surface of the star as well. And again, that's where all the important action is taking place in the context of the stellar dynamos. I just wanted to mention very briefly before I come to that, a few other applications of our data. I mean, not only can we learn about the internal structure of a star, its rotation, also as well activity. From our BiSON data, we get as well some other interesting applications. So essentially, because at each of our observatories, we're monitoring one of the data products we get out essentially is a measure of the intensity of the sun, so averaged over the disk of the sun over the course of the day. And our usable data we get essentially from days where we don't have substantial cloud. We can actually then get really good measures of atmospheric extinction and sky quality at these various observatories. So here's an example of a data set going back over 30 years or so at Azania, our site in Azania in Tenerife. And you can see here measuring the air mass and extinction and the air mass in magnitudes and the extinction. And you can see here these really, so this is an extreme example of an observatory where these are episodes of what are called Kalima. So this is where sand from the Sahara Desert basically blows out over the Canary Islands, and you basically pick up these really pronounced events where the extinction actually changes quite dramatically. Also as well, going back through the record, we can actually use these data to, for example, study properties of air particulates. So here's data where we've been able to measure, again, extinction, here splitting data into what we collect in the morning at the afternoon at our observatory in Las Campanas in Chile. And here, so some of you may remember the Mount Pinatubo eruption in the early 1990s. So here we pick that up. And you can measure, again, from the decay time here, you can measure and get lots of really interesting information about the particulates that were ejected into the atmosphere as a result of that. And also as well, how those particulates were actually carried by, of course, prevailing wind patterns and the prevailing circulation around the Earth as well, from actually looking at how this pattern, looking at lags in this pattern in the increase and the decrease for our different observatories that are spread around different longitudes. More recently, actually, we were able to pick up in our site in Narrabri in Australia, actually pick up as well. You remember the Australian bushfires So that's about a couple of years ago. There we picked up a clear signature of that, and also as well a significant signature actually at our site in Chile. So again, those particulates were basically carried across the Pacific, and we picked them up there. So there's lots of interesting stuff that we're doing with those data. Also as well, I should add as well a link to exoplanet research as well, where the variability that we get from these oscillations, which is the fantastic signal to us, if you're searching for exoplanets, that stuff is a bit of a pain in the bum. So also as well, we've been using our BiSON data as well to look at intelligent prescriptions for how we can actually essentially filter out those data in searches for exoplanets around other stars. But let's get back to the main point of what I want to go on and talk on the rest of the time here, and that's the impact that the changing activity in stars and sun-like stars has on the oscillation frequencies in particular. And of course, as well, so this is an example of a plot here of a sunspot records going back over 100 years. There's a lot of interest at the moment in these studies, in that, as I'm sure many of you will be aware, the last cycle, 24, was by far the weakest activity cycle, 11-year cycle, that we'd had during the modern satellite era. And you have to go back over 100 years to get to a cycle that had some sort of similar peak level. We're now on the rise of cycle 25, which is predicted to be, again, a weak cycle. There has been some very speculative, speculation about, are we heading into a grand minimum or not? And of course, that is driven by, if we look at reconstructions of the sunspot record using things like tree rings and ice cores, you can, well, actually these data here, I should say, are actually genuine sunspot records, but you can go back further as well, and you see other periods like the Maunder minimum and the Dalton minimum, where clearly the dynamo behavior of the sun was very different to what we see now, and periods where you get very little, if any, intrinsic variability due to spots. So we can be, because we've had, our wonderful satellite data for only a few solar cycles, there's a sort of tendency to get locked into the notion that that's how the sun has always been. And so one has to remember that that isn't necessarily typical. We've gone through a period of what's called the modern grand maximum. So what we're trying to do now is to use our helioseismic data to tell us something about what is it that is driving actually this reduction in the amplitudes of the solar cycle. What does that tell us about the dynamo action of the sun? And can we link that through to data on other stars to actually tell us something, to get, if you like, a wider, more holistic picture using other sun-like stars to not only tell us something about sun-like stars in general, but also to illuminate as well our understanding of the sun. Now, there's essentially what we're talking about when we're thinking about how this activity drives changes in the frequencies. Essentially, what it's doing here can happen in two ways. One, just through the action, directly by the action of the Lorentz force, essentially here, changing the frequencies of the oscillations. But also as well, you've got an indirect effect, those layers of the star where you've got these magnetic fields, it essentially changes the stratification there. And as a result, it changes the propagation of the sound waves through those regions, and hence as well the frequencies of the modes too. So you've got these two reasons why you'd expect, when you have changing patterns of magnetic field, is that those changing patterns not only over the surface of the sun, but also as well internally within the sun, that you might expect that to be driving changes in the frequencies of the oscillations of the sun. And that is indeed what we see. So this is a result from a very, very recent paper in which we had used data stretching back over 4 solar cycles. And what we did here is this is a plot here showing the frequency shifts that we see in microhertz, averaged over the most prominent modes of oscillation that we see on the sun. Again, these whole sun modes, so the modes that we would see if we were observing the sun as a distant star. The shift here is the order of peak to peak about 0.5 microhertz. Remember that the frequencies of these modes are around about 3000 microhertz. So these are parts in 10 to the 4 in terms of changes. Also shown on here, you can see as well, is what I've labeled as a best fitting model, and I will come back to this. This best fitting model, it sort of follows approximately the variation we would see if we looked at, for example, the variation of the sunspot number. So the frequencies that we're seeing to very first order looking here are approximately following the variation that we would see in the sunspot number or other global proxies of activity. But as we'll see in a moment, there are important differences, and that tells us something very interesting. This model here is actually a combination of a model that's saying that the frequency changes in some way that the modes are in some way sensitive to changes due to to activity that's seated in very strong field stuff like sunspots, and also activity that's related to weaker field stuff like network field and things called faculae. And I'll come back to what I mean by those shortly. This is a plot here where we're averaging changes over all the modes essentially that we can observe. But what we can do is we can also split down that variability by looking at modes in different frequency bands. So these are the different frequencies of the modes. So again, modes at the center of the spectrum have frequencies of about 3000 microhertz. So there, if you like, the intermediate frequency range, but we can also look at the shifts we see in modes that are at higher frequencies and lower frequencies. So that's the data here with some smoothing. What I've then done is to show as well, what we've done here is to take cycle 22. We've regressed the shifts that we see here against a global proxy of activity. So a really good global proxy of activity as well is, so I talked about the sunspot number. Another good one here is the 10.7 centimeter radio flux. So the sun is a radio emitter. So taking either that or the scale sunspot number, you can see a really strong correlation here in cycle 22. That carries on into cycle 23. And then you can see that for all three frequency bands here, the correlation starts to wander away. And it wanders away actually even earlier than that for the lowest frequency modes here. So this is sort of telling us already here that something that the frequencies in these global proxies of activity, while moving in lockstep in cycle 22, something happened during cycle 23, and that close correlation started to deviate. And it deviated most strongly in the low frequency modes. Now, this tells us something very interesting about what was happening in terms of magnetic field just beneath the surface of the sun. And the reason for that is that modes in these different frequency bands have a different sensitivity spatially to what is happening very, very close to the surface. And that's shown by these plots here. So these are sensitivity kernels for the modes in these different ranges. So the high, mid, and low frequency modes, plotted as a function of the fractional radius. So here we're looking at stuff really close to the surface. And for example, if I take here the solid curve, this is for the low frequency range. So this is giving us an idea of how sensitive the modes in that range would be to perturbations taking place within this outermost range of radii. And you can see here that they are very, very sensitive, and the sensitivity peaks at around about 0.99 something solar radii. But then you can see the sensitivity falls off as you get close to the surface. The mid and higher frequency range modes, however, have much more sensitivity, that right close to the visible surface, essentially the photospheric level. So what we think was happening here is that during this period, you'd expect that obviously we see magnetic phenomena at the surface of the sun, sunspots and stuff that pierces the surface. And of course, this is a result of magnetic buoyancy of the field, which is being reprocessed within the convection zone, then actually becoming buoyant and rising up and piercing through the surface. But there is going to be a reservoir of magnetic flux, of course, beneath the surface of the sun. And what we think this is telling us here is that actually that layer or reservoir of flux actually got thinner during this period. And as it got thinner, what it meant is that the low frequency modes here, which aren't sensitive to stuff really close to the surface, because that reservoir then was getting really scrunched up really close to the surface, these low frequency modes then started not really seeing any variation in frequency due to that magnetic field. And that's what we can see here. The low frequency stuff, it's varying nicely like the higher frequency modes are in cycle 23 to 22, but then suddenly that variability disappears in cycle 23 and cycle 24. So this is giving us really interesting insights in what was changing beneath the surface of the sun as we went into this cycle where things were, where the levels of activity were much, much lower. This was a paper actually we published in 2012. We followed this up in 5 years later and found that, if you like, that the behavior that we'd had, so let's go back to here, the behavior that we had in cycle 22 and the first part of cycle 23, which seemed to go out of lockstep, things have still not reset clearly. So something has changed, and that is really interesting, and we're trying to understand what that is at the moment. Okay, what I want to do now is connect in how we can...
Can I just ask a question before you change the subject?
Yeah, certainly, yeah.
Yeah, go back one slide there. So did you ever try to plot the size of the perturbation as a function of depth or versus, I mean, you know, you should be able to do that, right, from backing out.
So exactly. So that's something that we're doing now. So these sun as a star data, it's a little bit tricky to do that because you don't have, because you have so few modes here, even though it's a few tens of modes, the different angular degrees, which is really the thing that also is really helping you to give you that spatial resolution.
Yeah.
You don't have much range, but this sort of thing is being done with medium and high degree modes as well. Yeah.
Okay, I've forgotten you were doing, but you guys had the capability to do higher resolution things on the star.
Absolutely, yeah. So that's sort of that's the sort of thing that we're looking at the moment. Great question. Yeah.
So I'm thinking back to the stuff that Ken Lebrecht did in the 80s and 90s, where he had
exactly.
L's of a few thousand. What kind of L do you think you can reach?
So yeah, so we have, I mean, data that are collected regularly by so the Gong network, also as well other satellites as well. So the HMI instrument on the Solar Dynamics Observatory. There you get, you know, regular data products that come back, you know, with angular degrees well into the thousands. Yeah, and that gives you
that would be great to
spatial resolution. Yeah,
that would be great to understand what's going on here, because, right, I mean, you already remarked the likely candidate is changes in the magnetic field.
Yeah.
And when Ken first did this, I did some analysis with him, and it looked like basically the perturbation went like proportional to rho v squared, where v is the convective velocity and rho is the density. Yeah. So you think it was in, you know, that the magnetic fields were in turbulence, I mean, in equilibrium with the turbulence, roughly. But this says, well, unless you think the turbulence changed, which I find hard to believe, this says that that's not what's going on, or at least it's not so simple.
Yeah, exactly. Yeah, that's right.
That's really striking. Anyway, thanks.
Okay, so what we'll do now, let's bring in some data on other stars. And I'm just going to begin by showing you how the frequency shifts that we've measured on the sun, we can now do that on other stars. So I just want to concentrate first of all on the upper panels here. So these are two stars where what we've done here is to measure frequencies using the Kepler data over a period here of 1400 days. So what Kepler gave us was long continuity on stars. So of around about 3.5 years. Here again, this is showing the frequency shift average over the strongest modes that we see in these stars. Here are their HD numbers. So okay, just telephone numbers, but they're two essentially sun-like stars. And we're able to pick up this variability. Here there are two different techniques that have been used to measure the frequency shifts. So can we be sure that the shifts that we're seeing here really are associated with changes in activity? Well, obviously we aren't privy to be able to, of course, on these distant stars, be able to measure individual star spots. Well, we sort of can infer that, but that's another talk entirely. There are methods that you can sort of do that on some stars, but your sort of normal bog standard star, okay, you can't count sunspots, but you can see the variability due to star spots. And what that enables you to do is to actually build a sort of if you like, a sort of poor man's version of the sunspot proxy. So that's what's shown here on the bottom of the panel here. Proxies that have been built up by looking at the variability in the light curves of these stars due to the presence of things like star spots. And you can see that, for example, for this star on the left, as the frequencies increase, notice the change here is maybe about 3 times stronger than for the sun. You can see our proxy for activity increases as well. So how we're getting that is essentially it's activity-related modulation that we get because of the rotation of the star. So if we are in a position where we're actually observing the star essentially equator on, so the rotation axis is in the plane of the sky or close to the plane of the sky, as features due to activity, so spots, for example, which appear dark, they appear dark because convection is inhibited in those regions. As those sweep on and off the disk, we will see and of course that happens on modulo the period of the surface rotation period. We will see the brightness of the star modulated in a periodic way. So these are some light curves here of 3 different stars, actually showing stars that are more massive than the sun, more active with more rapid rotation period. So the solar rotation period is about a month. Here you can see a rotation period of the order of, well, you can see here a few days or a day or less. So really, really rapid rotators. You can build up a proxy then by essentially looking at the variability, the peak-to-peak variation or the variance in the light curve may be averaged over the rotation period, and that'll give you then a proxy for the activity in these stars. So that's what's plotted down here. So we clearly are picking up this seismic variability in these stars. And we can actually do it now. We've got the ability to do that thanks to the Kepler data, to do that over quite a number of stars. So here what I'm plotting in the top figure here is the seismic variability that we see in microhertz plotted as a function of rotation period. So why is that an important thing to plot against? Well, again, we have to think back to, of course, the origins of of activity in these sun-like stars. And again, the rotation playing a key role in the generation of that activity and the action of the dynamo. And the fact that as these stars evolve, the fact that we have these magnetic fields in the outer layers of the stars, that effectively the creation of that and a solar wind effectively acts as a lever arm or a brake to actually slow down the rotation. So over time, the canonical picture is thinking that these stars, they start off actively, they're rapidly rotating. Then what happens is that essentially they slow down over time and get less active. And this is sort of the picture that we're seeing here, right? As we go to the slower rotators, we're seeing a drop off in the seismic variability. And also as well from the seismic data, something I didn't mention at the outset, seismology gives us the ability to measure extremely precisely the ages of these stars. Okay, so from that as well, we can get a picture of the variability, the seismic variability, the activity of these stars dropping off with age as well, which is what we expect. I'm going to come back to these plots in a few slides' time because they actually tell us something else very interesting about the actual nature of activity on these stars, and I'll come back to that. So sort of leading into that, I just wanted to explain how we can actually measure so this is seismic variability. We come back here to measuring the variability of these stars due to this spot modulation or activity-related modulation. Again, a reminder that one way we can do that here, and that's how we get, this proxy here, is essentially from averaging over the rotation period, but measuring the variance as a function of time. But again, we average out the variation due to the rotation period, look at how that variance or range varies as a function of time, and we get plots that look like this. Okay, so here again, this is the fractional variability as a function of time, averaging out the rotation period, and you can see evidence of stellar cycles in these stars. So that's one way of getting a handle on stellar cycle variability from the impact of spots, other active features on the surface of the star. But one other way of doing this is to actually measure the change in the absolute level of the detected flux of the star. Now, this is a hell of a lot harder to do because you have to normalize out for a lot of systematic effects, instrumental effects. It's incredibly difficult to do. But some people have done it. So Ben Montet and his colleagues did a great job of doing this. So here, instead of measuring the variance around the mean, here what you're doing here is measuring the absolute variability. And if you do that as a function of time, here's a selection of stars, it gives you another way of actually picking up the variability.
Can I just interrupt again? Are these solar type stars?
Yes, they are. Yeah, they are.
Because like my recollection is the sun is like a part in 10 of the 4, and these are 100 times bigger variations, right?
Yeah, so they are. I mean, they're certainly more active, so they're much younger in these.
They're younger. Okay. All right. Good.
Yeah.
Thanks.
I guess while we're asking questions, for the younger and faster rotating stars, couple of things. You must be then seeing more dynamo cycles.
Yes, correct. Yeah, they're shorter. Exactly. Yeah.
And are you able to then get better statistics on aperiodicities and or how periodic the dynamo is?
Yeah, so I think so it's right. So it's true that we're sort of, because the Kepler data are only 4 years long. For a star like the Sun, we'd only sample part of the cycle,
right.
But a lot of the stars we've been looking at, have periods of sort of a year or less. And in some of them, you pick up variability. I mean, you can sort of see it in some of these examples here. There are some stars where things will go through sort of ambient periods, and then you'll pick up variability. So it's quite a menagerie, I guess, of different types of variability. And people who are working on this sort of stuff, of looking at the full range of data that we have on different stars, it's a case now of actually trying to get as much other information as we can on these stars. So for us, we're doing it with seismology to be able to help us make sense of some of these patterns of variability that we're seeing.
And so the related quick question is, you must have then, with the ages, better tests of Skuminich.
Yes, exactly. And actually, I've been involved in some of that work, and it actually shows that that sort of spin down something strange seems to happen to that about the age of the Sun. And the Sun seems to be an important sort of transitional age where the brake stops working as effectively, that magnetic brake, which is really interesting. Yeah. So having these two different ways of measuring the variability, one, the variance around the mean, one, the absolute level, actually gives us complementary information. And here we just need to think about the two types of activity that you might expect to dominate the variations in brightness. So one are spots. So spots are dark. Again, they tend to big features with strong magnetic fields. Again, dark because convection is inhibited. Also, as well, we see these things called faculae. So faculae are bright. So again, they're tubes of magnetic flux, but they have a much smaller cross section. They appear bright because the walls of the tube get heated. And so again, convection is inhibited, but the walls of the tube are heated from the surrounding regions, and that heats the insides of these things, and they end up looking bright. Imagine you have a star that is spot dominated. If a star is spot dominated, as it gets more active and you get more spots, the variance method will show the variance increasing. The absolute method of measuring the variability will show that the absolute brightness of the star will decrease. If, on the other hand, you have a star that is faculae dominated, as it gets more active, you get more faculae, so you get more variability, more variance, but also you'd expect the absolute brightness of the star this time to increase and not decrease. So what you can do, if you can measure the variability in stars in those two different ways, you can then get a handle. And also, of course, you get the rotation period from the variance method as well. You can get a handle then on looking at whether or not your stars are faculae or facular or spot dominated, and how that varies with rotation period. And so Ben Montet and his colleagues, what they did, they basically found that you got this really, really nice sort of demarcation of the longer period stuff being facular dominated, the shorter period stuff being spot dominated. And the Sun, which has a rotation period sort of around about here, is in sort of the transition from going from spot to facular dominated. Now, why is this interesting in the context of the seismic data? The seismic data fit this picture really quite nicely. So again, the notion here again is this is sort of the rotation period axis here. It's not quite literally, but it's sort of here mapping onto evolution as things on the whole, all of the things being equal. It's suggesting that you'd expect stars as they evolve to transition from being spot dominated to facular dominated. Remember this plot I showed in the model I mentioned, and I said that this was a model where we tried to model the frequency shifts in terms of being some combination of sensitivity to weak flux, so facular stuff in sort of general terms, and sensitivity due to strong field stuff, sunspots. Now, what we can do with the sun is we can actually, because we can actually resolve the sun, we can from magnetograms, we can actually work out the amount of flux that's tied up in the weaker stuff, the amount of flux that's tied up in the stronger stuff, and therefore do a model regression of the frequency shifts on a model that has those two different components. What we find interestingly for the sun is that these whole sun modes seem to be a heck of a lot more sensitive to the strong stuff than they are to the weak stuff. So that model seems to be suggestive that it's the changes that we have tied up in the flux in the sunspots that seems to be driving the changes in frequency, not the much more weaker field stuff. And there's a lot of it. There's a lot of flux tied up in the faculae, even though individual faculae, the magnetic fields associated with them are much, much lower. But it seems like it's the strong field stuff that's driving these changes. So what that suggests then is, if we come back to here, remember what we're seeing here, the seismic variability, is we see most of the seismic variability in stars with shorter rotation periods, not the long rotating period stuff. Again, stars that are younger, not older. This sort of ties in with this picture here. Again, remember here that it's the spot dominated stars that are the more rapid rotators. The facular ones are the longer period rotators. The seismic variability we're seeing is all in the shorter rotation period stuff. And that's kind of what we'd expect to see if what we see on the sun is correct, and that we really would only expect to see measurable variability in these other stars, seismic variability, if it's tied up in stars that are spot dominated. And that's kind of what we seem to be seeing. So that's one interesting result. I just wanted to finish up, and I'll go through this quickly because I'm mindful my time is running out and I'm probably already going over the time I'm supposed to be taking on the talk, so apologies. So we're eating into time for questions.
You're okay, Bill, carry on, no worries. We've got till the end.
Okay, thanks. We can also use the data on the oscillations to say something about the active latitudes on stars. So here's a really nice picture. This is a sort of time-lapse composite image of, coronal emission on the sun, rotation axis pointing up, equator here, and picking up the active latitudes that we see on the sun. The reason we can do this is because the non-radial modes have spatial sensitivities across the surface of the star, across the surface of the sun, which are latitudinally dependent. So here are some examples of mode patterns for modes of different angular degree L and azimuthal order M. So the degeneracy, so in M, so that's lifted basically by rotation, essentially. So you can see you get all these different patterns. And if you look at the example here, the Terry's chocolate orange pattern of angular degree azimuthal order 10 and 10, you can see from the contours here, most of the sensitivity here is concentrated nearer the equator of the star. Now, the Terry's chocolate orange and also this mode here are modes that we don't see when we observe these other slowly rotating sun-like stars, because we only pick up modes that have low angular degrees. Okay, what happens in the high angular degree modes is that because the spatial patterns are more complex, we have many more regions that are either brighter or darker on the surface of the star due to the oscillational perturbations. And those perturbations tend to cancel out in the higher degree modes. So we tend to be just seeing the lower degree modes here. But even in the lower degree modes, we have some latitudinal sensitivity. So in particular, if you look at the L2, M2 mode here, you can see here most of the peak sensitivity again is peaked near the equator. If we look here at the so-called zonal mode, so the 2-0 mode, L equals 2, M equals 0. So you can see again here, well, it's got more sensitivity up near the poles as well. So there is some spatial sensitivity in these modes, and if we can actually measure the frequency shift of over time in these different modes, these modes of different angular degree, it in principle gives us some sensitivity to the latitudinal dependence of the activity. So I think it's the only slide I have with an equation on. So essentially here, what we're doing here is we're saying the frequency shifts here that we measure, there's some normalization factor here, that's the observable. There's some normalization factor here, which I don't care about here in the discussion. Essentially, this is going to depend on the spherical harmonic of the mode, so its sensitivity. So you basically get that these are Legendre polynomials. So again, we're decomposing these modes onto spherical harmonics. So we've got the Legendre polynomial here. That's essentially giving us the latitudinal sensitivity of the mode. And this stuff over here, which is basically the B field here, the variation of that with co-latitude. How is that distributed across the surface of your star? Okay. So if we've got this observable, we know which modes we're using. So in principle, we can unpick this activity distribution. But of course, we have to do this. We have to constrain things and simplify the model. So we've got a shot at saying something meaningful. So what we've done here is to do this analysis, assuming that we're modeling the active region, the bit where we get the perturbation, as a slab of activity here that runs, that's the orange bit here, that runs between some minimum and maximum latitudinal angle. Okay.
Sorry, I have to ask, I got confused by the equation. If you go back to one slide, why is it p squared? Why is it not linear power? Because in which case we'll cancel that exactly.
So here this depends upon how you assume the frequencies depend on the field, essentially.
Yeah, that's right.
Okay.
So why is it squared?
So the squared, so this comes back to, I think, a lot of the analysis that's been done actually with a high degree mode. So actually Norman's question from earlier suggests that the squared dependence actually gives you the better fit to what you're seeing rather than just a linear.
Oh, so this is not the theory.
Yeah.
Oh, okay, thanks.
So if we take this model and we, so actually I should probably just go back to here again. If we can actually measure the frequency shifts, again, what we do is we average over the frequencies of the modes. But what we do is, for example, we say measure all the frequency shifts of the L=1 modes and the L=2 modes. Okay, and we also are able to as well separate out as well the different azimuthal orders as well, because they have different, which I won't go into the detail of this, we can pick this up in the questions, but there's basically, we have the ability to basically separate out observable frequency shifts of different combinations of L and M. If you have a star where activity is concentrated in the active latitudes, you'd expect, for example, the frequency shifts measured by the L=2, M=2 modes that have more sensitivity near the equator to be stronger than the shifts that you measure in the L=2, M=0 modes. Okay, which have less sensitivity, relatively speaking, in those regions. So what we've done is we've done this for the BiSON data. Here, what you can then do essentially is then infer what the activity distribution is. So we just use a sampling algorithm to do this, taking the observable, our known harmonics, because we know which modes we're using, and we can then make an inference from the data on what the minimum and maximum active latitudes are. This is what we get from using data on the sun, using just 4 years, essentially what we would get from Kepler. And essentially what we find then is that we get an inference on the minimum latitude of the active belt, which is basically, you can see here, is peaked near the equator, which is what we see for the sun. And then the latitude, the maximum latitude of the activity on the sun here, it's suggesting a latitude of around about 40 degrees, something like that. Now that's slightly higher than one might expect naively from the distributions of the latitudes of sunspots. However, if you actually look at the latitudinal distribution of magnetic flux through the cycle on the sun, what you find is that does bleed through to higher latitudes. And essentially our analysis, what we know from comparing the results here with what we actually see on the sun, this is telling us here that our analysis is basically telling us where the strong magnetic flux is basically merging into the much more widely distributed weaker network flux. But nevertheless, you can see just from these few angular degrees that we're seeing on distant stars, we can actually say something meaningful and sensible about where the active latitudes are on the sun. So just to finish up, let's try it for another star. So this star that I showed earlier, one of the two stars, so we tried this on this star here, which is HD 173701. We had the data to be able to do that. We could measure the frequency shifts in different angular degrees. Here's the result we got. Interestingly, a bit different to the sun. The latitudes seem to be shifted basically upwards to higher latitudes. The minimum, so where the slab of activity runs from, the minimum latitude is pushed higher up to about 20 degrees. The peak, the top of the band, essentially, you can see here is up at a much higher latitude again on the sun, sort of 30-40 degrees, here up around 70 degrees. And just to show those two distributions, the orange actually it's more a kind of pinky color, isn't it, with the sun, and the bluer color here with this particular star. Very, very different. Now, this particular star here, if you were to look at its age, if you were to look at its mass and look at its radius, it kind of looks pretty sun-like. But if you actually look at the frequency shifts it's showing, they seem to be stronger. Also, as well, if you look at the surface pattern of differential rotation, seems to be different as well to the sun. That we think is, when we're still trying to understand these results, that there's something, there's something very interesting to say there around. And we'd expect, how the rotation varies with latitude and also with depth, for that to have some bearing on the active behavior of stars. And that seems to be borne out by the result that we have here on this particular star. So we're trying to do this now for other stars, both with the Kepler data, but also with data from the NASA TESS mission as well, which is giving us data on a larger number of these sun-like stars. Also as well, with a view as well to connecting this back to and using the BiSON data to be able to, when we make these inferences and do these analysis on other stars, using the BiSON data to basically benchmark these analyses. Right, with apologies for going over, sorry, I think I'm right at the hour. I will stop at that point. Thanks.
Okay, Will, perfectly timed. We'll give you a quick Zoom round of applause. That was great. Thank you very much. We've got time for a couple of questions. Officially, we should end at the hour, but if people need to go, they can. And if people want to stay and ask questions, that's fine. So, Chris, do you want to go ahead?
Quick question: what are the prospects for a very long-term, decades-long, space observatory that could really dig to these cycles? And
I think, well, the closest thing that's on the cards coming up is the Plato mission, European Space Agency Plato mission, which will combine, I guess, the sort of, well, the good attributes of attribute of Kepler in this respect, which is the long time base. Now, the nominal mission for Plato will comprise probably some step and stair type phases, but with probably an initial phase of 3 years. The good thing about Plato is it has a much wider field of view than Kepler did. So Kepler was looking at a very small patch of sky. TESS has a much wider field of view, but also, of course, it's observing many more patches of the sky, which means it doesn't have quite the same continuity, although it does revisit parts of the sky. So I think Plato will give us prospects for adding multiple year data on these stars, and also it's got a pretty similar seismic sensitivity in terms of apparent magnitude. So we'll be revisiting some of these stars. That's the crucial thing. The other thing about TESS is we will be going back to some of these stars, and hopefully for many more years to come. I think TESS has fairly low demands in terms of its consumables. And if it continues to get funded, obviously it will require approval through a succession of senior reviews to do that. But it could carry on taking data maybe comfortably for another 10 or more years or more. And the good news is that mission is, in terms of the resources it needs, but also the ground-based resources that are needed to keep that thing going, it's not a really big mission. So yeah, I think the future's quite bright.
Great. JJ, do you want to go ahead and with your raised hand?
Yeah, thank you, Bill, for a really nice talk. So I had a question related to one of the second inferences you talked about. So I believe you talked a lot about how the magnetic fields change pressure modes because the main restoring force is pressure, and magnetic fields basically change that a little bit. But you didn't talk a lot, I think, about how magnetic fields can potentially change the internal stratification, and that would potentially be really powerful because you can probe gravity modes, and that can probe the magnetic fields of the interiors of stars. Could you talk a little bit more about efforts to constrain magnetic fields using gravity modes?
No, that's
Okay.
my
Yeah.
ignorance. So, good question. I think certainly from the perspective of trying to, so obviously I didn't really say much. I didn't say anything about what we're doing with say high degree modes in the context of the sun. And there we are able to sort of go into depth with the sort of things that you're talking about there. I think with, so it is in principle possible to do this with a bit more clarity and some, a bit more fidelity maybe in terms of being able to have a bit more spatial resolution, probably in slightly hotter stars, things like Delta Scutis, where you do have access to high degree modes. The problem there is actually making sense of and interpreting what you're seeing. And obviously there we're going to much hotter stars which don't have convective envelopes. So it does tend to be the case that the stars where predominantly most of the modes that you observe are buoyancy modes tend to be the hotter ones that don't have outer convective envelopes. And of course, the sensitivity of the modes for stars like the sun, when they evolve to become subgiants and red giants, there we do see really rich observable signatures of buoyancy modes. But of course, the sensitivity kernels for those modes tend to be, of course, much more peaked towards the center of the star rather than the surface. So it's a bit tricky. But
related to that, when are we going to see gravity mode from the sun?
Oh, that's a good question.
You must know among anybody else, right? Among everything.
I don't know. I don't know about that. Okay, so there have been claims of this. There were claims dating back a decade of seeing signatures, ensemble signatures. Much more recently, quite a clever analysis that was done that claimed seeing signatures of gravity modes through the impact that they have actually on a periodic change in stratification that affects the cavities of P modes. So you actually pick up the signatures of G modes through subtle changes in the pressure modes. That analysis is really clever, actually. It's very clever. It's done by a guy called Eric Fossar, who's one of the sort of founding figures of the helioseismology field. So it's a really clever analysis. Personally, I'm extremely skeptical. So I think the claims that have been made, I don't believe.
Right.
They know that. I think it's going to be tough for us. I mean, lots of efforts being made. Actually, his analysis actually was good and claiming that it reinvigorated efforts to understand, well, to try and also as well what we've been doing with Kepler and other stars. It's reinvigorated our efforts in terms of the analysis we're doing, but also it's reinvigorated efforts, I think, to get a better theoretical handle on what the actual geomode amplitudes might be. But my feeling is we're probably, we're trying, but I don't think I don't believe the claims that have been made so far. Yeah.
Okay, Stefan, did you want to go ahead?
Yes, is anything being done on close binary stars, oscillations on close binary stars?
Yeah, quite a bit with Kepler. So there are examples, so-called heartbeat stars, which show these really, which actually where you can clearly see really pronounced changes in the seismic behavior of those stars as a result of the interactions between them. Yeah, so if you look at they're sort of colloquially termed heartbeat stars.
Right. Really
rich stuff that's done there. So some of my British, actually he's no longer based in the UK now, but Don Kurtz. Some of you might have heard that name. So Don is someone who is one of the sort of the key people for those analyses and discoveries.
Cool.
You could make one comment that in studying spots on close binary stars, eclipsing stars, short period ones, analyzing the light curves, most studies seem to show a lot of spots near the poles of these stars. So I was rather intrigued by your result, but there's rather high distribution of spots on the HD173, whatever. because there certainly is a lot of these results of them have shown that these spots do seem to be spotted on the near the poles. It's sort of odd. Anyway.
So I had a question related to that. You said you showed some data indicating that it was again a solar type star, I believe, but you had you inferred a high latitude for the spots. And what I was trying to remember was, I mean, the solar field, there is a dipole field of the sun, and I remember I tried to measure it years ago. It was of order of Gauss.
Yeah.
So not that different than the Earth, but of course larger scale. And then I was trying to remember the spin down. Is it like, what's the Alphane radius for the magnetic field in the sun? My recollection is it's like, you know, a couple stellar radii. It's pretty far out.
It's more like 10. It's about 10.
Is it 10? 10?
It's about 10.
There was a good measurement recently, yeah. So that's got to be the dipole part of the field. Well, split monopole, if you think of it as a wind. But the fields you're looking at, the variations are about, as I said, 100 times higher in the frequency. So the field, well, did you try to infer a field from that? And then the next question is, okay, is it more of the field in these stars in the dipole component? Because in the sun, it's not in the dipole, right? Most of the field's actually in a higher.
Yeah, our inference is it's basically the toroidal stuff, right? That's tied up in the spots essentially that's driving this. And that when you transition to, well, we see it clearly in the sun, but also in these other stars clearly, when you transition to a phase where you don't see pronounced signatures of spots. And we know, as I should add as well, that we know in these stars, we can say something as well about the angle of inclination of the star as well from the seismology.
Yeah.
So we know that we're looking at a edge on. We know therefore that the dominant variability we're seeing must be from sort of spot-like stuff, and there must be a reasonable amount of it. You know, it can't all be really, really close to the equator, otherwise we wouldn't see the sort of clear modulation of it. So I think the inference is that, yeah, it has to be the toroidal stuff that you're seeing, and it kind of has to be, again, from what we know of the sun, to be able to see the sort of measurable frequency changes that we see that are pretty much like the sun, or maybe a bit stronger. It has to be that strong stuff. Yeah.
So I'm just wondering about, right, the Schemanisch law says you spin down fast when you're young, and you do have stronger fields. Is it just the field strength that matters, or is it the actual shape of the field also makes a difference? I don't know if you've thought about that at all.
Yeah, that's a good question. Probably an element of both, I would imagine, but yeah, I think.
I'm just thinking you might be able to try to address this question with your data.
Yeah, that's right. Yeah, that is an interesting thought.
Probably has something to do with the transition from spots to faculae.
Indeed. I was thinking of that as well.
Yeah, that's right.
I mean, we don't know a damn thing basically about the stellar dynamos, is what I would say. and this would be a way of getting at it.
Yeah, well, I agree with you. I mean, I think having more, we really do need more observational constraints on this stuff. And yeah, exactly. Having it from, I guess a lot of it is relied on just one data point, right? The sun. Exactly.
And now you've got data that's, you know, not as good as what we have for the sun, but it's not so bad.
Yeah.
It's really cool. Great talk, by the way.
Thank you.
Yeah. Thanks very much, Bill. I feel like we should probably let you go, as soon as it's a bit later on for you. Unless, Yamcha, did you have a quick question? You put your hand up a minute there, and I think it went down again. But
no, I think that was really puzzling. So how is the magnetic field? Yeah, the activity cycle and so on changing the frequency. I don't get a good sense of how do you calculate it, because it's all small scale field. And is it convective flux also changing during that time, or how would you even?
Well, in the sun, it is. Well, so there's these papers I did with Peter where we sort of worked out how the flux would change the frequencies, and it looked to be about right.
You mean the convective flux change in that small scale spot region? That's what's changing the frequency?
Well, that we couldn't tell whether it was, so Bill already indicated, right? There's the direct effect of, you know, the magnetic field will stiffen up the response to the gas, so that changes the propagation speed directly.
But that would be a toroidal field you're talking about.
Well, no, it depends. It could be either way, right? I mean, he's talking about things that are pretty shallow, so they're moving horizontally a lot of the time.
That's right.
But then there's also, so two other effects. One is you can actually, because they block the convection, you change the temperature. So that changes
Right.
the sound speed,
That's right.
which does change the propagation speed because it's a some combination of B squared and CS squared, right?
But still
and
in
then-
small scale, right? Not in the global sense.
No, it's a global change. You can see that on the sun, right? Because if you
I
look
mean,
at
the toroidal field has a global change during the solar
oh yeah,
cycle.
Yeah.
and
I see.
the brightness of the star changes as well. So he showed you the full sun.
Not
But
in the
if-
case of sun, like that's not
Yeah.
big, right?
Oh yeah,
Like you
no,
said, part and 10
No, but that the changes in the frequency are not that, they're of that order, right? It's
Yeah.
microgauss out of milligauss. So it's
I see.
comparable.
I
Yeah.
see.
And so
Okay,
untangling
it's just
these,
that
there-
it's just a sound speed change for the part and
no, it could also be, if you change the temperature, you change the
Mhm.
scale height of the gas. So you change the size of the cavity.
Right.
And they go in
Okay,
the
so
opposite
two things.
sense.
Okay.
And we could never figure out
Yeah.
which one was dominating. And I don't know
I
if anybody's
see.
paid any attention since then.
So it's
I
not a
think
field. So go ahead. Yeah.
There's still an open question, I think. I don't think anyone's really got to the bottom of that. Yeah.
So it's not a direct change of, say, Lorentz force. That's,
Well, that's part of it.
but that what you're talking about is all gas property change, not Lorentz force, right?
Well, no, the one where I said it's just directly B squared, that's the Lorentz force part, right?
Well, the B squared is through gas pressure, but okay, yeah.
Well, it's
I
not
see.
a gas pressure, right? You're
I
trying to
see.
squeeze the stuff and it's tied in the magnetic
Mhm,
field. So you're trying to squeeze the
mhm,
magnetic field and the magnetic field doesn't like that, right? So
Mhm,
it pushes back.
mhm, mhm.
Do you remember Norman Phil Goody and
Yes, absolutely.
Wojciech Jimbowski? So they did some stuff. God, I'm trying to think their papers somewhere in the 2000s, I think, where their analysis suggested that maybe it was a bit more of the indirect than the direct, but again, there's maybe some frequency dependence in there, but still pretty sketchy, I think. So
Mm.
It was hard to try to think about how to disentangle all this stuff. And there was really good data from the sun, that, the
Yeah.
very spatially resolved stuff. But, having these different stars with different distributions of magnetic field, I mean, that's just like, then you could really try to think about how to do this.
yeah, exactly.
So I do have a question on that related to that. So you show this extreme flux variation in stars. So you can really get an ice age from 2% change in solar flux. So is that common?
Well, you weren't as high as 2%, were you? Oh,
Yeah,
no,
so-
you were. It
yeah,
was of order of
Yeah,
percentage.
that's serious for climate modeling. People claim it's climate change because of solar cycle, which is loony here. But in those planets, it may actually well be. So
they're
is
quite-
that? Mhm.
They're quite. Those are examples that are, I guess, a bit more at the extreme end of
They're
the
more
scale.
extreme.
Yeah, I think just to make from the paper, just to make nice plots.
But
no,
put the
that sounds a
sun,
bit
put the
That's
younger
a bit
sun.
pejorative, isn't it? But
No, I like it though. So, well, I mean, to see these extreme examples is instructive, right?
exactly.
But the question is, would the young sun behave like that?
Probably did.
But then it would be interesting climate change wise, right? In the sense
Well,
that,
but you're
Mhm.
talking things that are less than 1 billion years old, probably, those stars, or do you have a
Yeah, they would
reflection?
be. Yeah, for sure. Yeah.
well, but
I mean,
that's
the first-
very, you can
first
cause
billion
climate
years-
oscillations using 2% flux variation, which could have, instabilities or things like that related to it.
No, all I was going to say was, right,
Mhm.
there was a lot of other nasty stuff going on in the first 1 billion years of our evolution. So just me, it'll be a problem. but
Probably
there may
worse
be
than
other
2%.
bigger problems. Yeah, exactly.
Probably, but the 2% is quite interesting. 2% is interesting. If it's
No,
much
but
less,
remember
who
that it
cares,
was
right?
30% less luminous, our sun. So why weren't we a snowball?
Well, there's the issue that why we're not in the slow ball, but if there are oscillation like that,
No, it's
Who
true.
knows?
It is good to think about. So that's a good
right,
point.
it's actually really interesting. So with the more data we get, we know about the young sun. Yeah. Anyway, that was really interesting talk. Thanks, Bill.
Yeah, thanks very much, Bill. That was really great. Good to see you again.
Yeah, good to see you, Ted. Yeah, thank you. Thanks everyone for
Thanks.
joining.